I want to begin by talking about the resources that I relied upon in creating this lecture. Primary resource for me is a book called Data Modeling, A Beginner's Guide by Andy Oppel. This is a book that I've used in several of my courses. It may not be the core, it may not be the data modeling text that we're using for the course that you're taking, but it's a book that's worth having, and I recommend it to you. Just to click through on the link in Amazon. You can buy this book in paperback for less than $30. So I think it's a pretty good investment. So that's where a lot of my content has come primarily from chapters 2 and 3 in the Andy Oppel book. Okay, next, let's answer the question, why do conceptual data modeling at all? Okay, why do we do this activity? Well, I think you can kind of come at it from two perspectives. Okay, you might be a systems analyst who is responsible for um, uncovering and documenting the requirements for a computer system, a system solution that will solve some kind of problem or capitalize on an opportunity for people in your organization or your client organization. Okay, that's our first possibility. And people in my systems analysis and design course are in just that, just those circumstances. And what do we learn how to do in my systems analysis course? Well, we learn how to identify and document the requirements for the system from four perspectives. Perspective one, we would call that process requirements. And the approach that we take to those include use cases and user stories. Okay. The second part, data requirements. And the approach that we take to that, conceptual data modeling. So that's how we got here. User interface requirements, non-functional requirements. So we address the requirements for the system from four perspectives, and when we address the data perspective, we're doing conceptual data modeling. So that's how we got here. What if you're in one of my other courses though? Okay. You're probably at the beginning of a three-part database design process for a relational database. Okay? And how do people typically do that? Well, they do three steps: conceptual data modeling, logical database design, and physical database design. Why do they do it in three steps? Well, because we've been doing that way for a long time, 40 or 50 years, and it seems to work well. Okay. Now, why does it work well? Good, because telling people that it works well, that kind of begs the question. I think it works well for a couple of reasons. One is that the audience for each of these design artifacts is slightly different. The primary audience for a conceptual data model are user people and the stakeholders involved in documenting the requirements for the project. When we get to logical database design, the primary audience for that design is going to be the system developers. Yeah, the people who were involved with the conceptual data model are going to want to see it because they're going to want to make sure that we didn't change it a lot, okay? But it's largely the developers. The physical database design is certainly of interest to the developers, but also people with responsibilities like database administrator, okay, or um, enterprise architect, those kinds of people. One reason that we do it in three parts is that each of the parts gets more specific and detailed. It gets more specific in terms of you can do a conceptual data model, and then you could decide to do a relational database, or you could decide to do a a NoSQL database. You could decide to do some other kind of data store altogether. Okay. When you get to logical database design, you pick the technology. You're either doing relational databases, or you're doing NoSQL databases, or some other technology. Logical database designs are technology specific. And then physical database designs are not only technology specific, but they're product specific as well. Okay. Because of this, if you jumble all this together, you'll wind up having to back up a lot, and you'll have a lot of rework. So this three-part approach to database design has been kind of tried and true for 40 or 50 years, and it's been very popular, and it's basically what people do. So right now, today in the lecture, we're going to be talking about conceptual data modeling. Okay? Let's talk about the tools and the notation that we use for conceptual data modeling. Okay. Now, you can actually express a conceptual data model using a couple of different kinds of diagrams. The most popular of these is an ERD, or entity relationship diagram, and that's what we use in my courses. So let's take a peek at what they look like. Here's an ERD that I created to show students in one of my courses within the last year, and it's designed for an e-commerce database for order processing, and we have customers, and we have orders, and then for each order we have a bunch of order lines, and each order line is for a particular product, and each order can have each order has a shipping address and a billing address. Okay, now, are you supposed to understand all the notation right now? Well, not yet, but we'll be getting there soon. All right, so that's where we're headed. The notation that you saw there is the information engineering format for ERDs, or the IE format, with a little bit of creative license. The problem is that each diagrammer that you might choose to use draws things a little differently. And the diagrammer that we're using in this course at this point is Lucid Chart. We're using, in the fall of 2021, as I record this, we're using the free educational version of Lucid Chart. And with a little bit of license, we can do the IE format for ERDs. One thing I want to point out is we're not using the format of the original ERDs as uh, uh, developed or invented by Professor Peter Chen. A lot of people in, a lot of textbooks used at universities and some courses. The people in higher education are fairly fond of the notation that came from Peter Chen. Uh, it's really not used a lot in industry. And in fact, this information engineering notation is probably the most popular one used in industry. And that's why we've decided to use it in our course. All right. The bulk of the lecture is going to be about ERD components. And these are entities, relationships, and attributes. And we're going to talk about each of those in turn. So we're going to begin by talking about entities. So let's begin with entity basics. So what is an entity? An entity is a person, place, thing, event, or concept about which data is collected. And I borrowed that from Andy Apple's book. So examples of entities would include employee, city, product, concert. And the names of entities are usually singular nouns: customer, order, product. How do we represent entities on the ERD? Well, as a rectangle that we label with the name of the entity. So let's take a peek at that. Okay, so here are three different ways to draw an employee entity. Okay, so we have a rectangle. It's got rounded corners. That's not really important. Okay, that's just kind of the style of the shapes that came with Lucidchart. It has more to do with the artwork of the day than anything else. So the one on the left here is the employee entity on a diagram where we're not going to show anything but the entities and the relationships. Now we don't see relationships here yet, but it doesn't have room for these things called attributes. Okay. The one in the middle is from a diagram that is going to show attributes, and the white space here is where the text is going to go that gives us the attribute information. And the one on the right is actually the one that we're going to use in our course for conceptual data modeling. And it's going to give us, it's going to allow us to create the diagram in a way that we're going to be able to easily transform it if we were to transform our conceptual data model into a logical database design, which in 2 of the 3 courses I'm doing this for is something that we're going to do. Okay, so these are 3 ways that entities might appear on an ERD. Okay, now more about entities. Okay, even though data modelers, and that's what we're learning to be here, even though data modelers usually call these entities, it's important for us to remember that the entities that appear on ERDs are really entity types, and they have type instance semantics. Okay, so this thing that we're drawing on the diagram is the entity type. It is not an entity instance or instances. So city could be an entity type. Okay. What would be an instance of the city entity type? Well, Milwaukee would be an instance of the city entity type. And Milwaukee is not going to appear on the ERD, but city will. So let's look at that and kind of try to understand the distinction. So here on the left side is an entity box uh, from a conceptual data model for the entity type city. Okay, and on the right hand side, I have a table from a relational database. It's implemented, and let's say we printed this out using the tools that came with the relational database. And the city entity type has become a city table in the relational database. And it has columns, which we're going to find out later are sort of the implementation of attributes from the conceptual data model. And each row in a relational database table represents one instance of the entity type. Okay, so we have entity types on ERDs. We don't have instances. They don't appear, instances don't appear on ERDs, just the types appear on ERDs. Okay, and then when we finally build a data store, okay, the data store is going to hold the data for the instances. And in this case, if it's going to be a relational database, it's going to be a table, and each row is going to be an instance. So Milwaukee would be in the row with city ID 2. Okay? Now, having said that, okay, that these are really entity instances, I want to point out that practitioners call these entities. Well, why do they do that? Well, I think it has to do with kind of shop talk. So, in most professions, we have kind of shorthand ways that we talk about things, and we try not to have too many words for things. And on the ERD, we're only showing types of things, as we're going to see. So since we only show entity types, do people have to say entity type all, every time they say it? Or could they just say entity? Well, the fact is they just say entity, okay? But don't forget, these are entity types. Okay, let's talk about relationships. Okay, so let's talk about the basics of relationships. So Andy Oppel, in his book, says relationships are the association among entities. What are some examples of relationships? Well, employed by, has player, has ingredient. Okay, well, what do they look like? Well, relationships on an ERD are represented by lines that connect the entity boxes. Let's look at these. Okay, so here we have three entity types, or as data modelers are likely to say, three entities. Okay, and they are connected by relationships. Okay, so the coach and the team entities are connected by a coach's relationship, whereby we would say that a coach coaches a team, and the player and the team are connected by a plays for relationship, whereby we would say that the player plays for the team. Okay? Now, a couple of little details to call to your attention here. Um, like we said a little while ago, the entities are typically given singular noun names: coach, team, player. Okay? Why are they singular? Well, they're singular because we wanted to be able to say that an instance is a type. So we want to be able to say the Milwaukee Bucks, I guess it would be our team, or uh, Tom Smith is a coach, right? So we want to be able to use that is a. Okay, so Tom Smith, it's not the case that Tom Smith is a coaches. No, Tom Smith is a coach. Okay. Um, these relationships are typically given names that are either verbs like coaches or verb phrases like plays for. All right. Now, when you really think about how we name these things, it can be challenging. Okay. And with a little bit of advice, you can avoid the challenging aspects. Really descriptive relationship names are usually only completely true in one direction. So, for instance, coach coaches team. Now, read it in the other direction. Team coaches the coach. No, that doesn't seem to work. That seems to only be true in one of the directions. Okay? Now, there are practitioners who, because of this, they come up with two names, one to use in each of the directions. Well, you just get a proliferation of names. Okay, so here are some ideas. Uh, Normally, relationship names, when they're descriptive, are directional. Okay, so how do people solve that? Well, here's what some people do. They use directional names, but two of them. One that's going to be true from each of the directions. A problem with that? Too many names. Okay, here's another solution. Uh, Pick a name that's non-directional. Uh, uh, Coaching ship. Okay, you can try to come up with a non-directional kind of a name. Those names are just not really descriptive. So the third option is the one that we follow in my class, and most practitioners seem to follow this, is you pick a directional name, okay, one of the two available, and you stick to it, okay, with the understanding that, kind of underlying that is the opposite directional name, but we're just going to pick one, all right? So, in terms of a coach and team, we picked coaches. In terms of player and team, we picked plays for. Okay? We're not going to do two names unless we absolutely have to. I'll show you an instance, towards the end of the lecture, in which I'm saying that maybe we would want to go to two names for the relationship. Okay? But not here. All right. Let's move on. Relationships are usually, the names are either verbs or verb phrases. We're not going to name them in two directions, just one. and it's going to be a direction-oriented name. We're just going to pick the one that we want. Very good. Let's talk a little bit more about relationships. Okay. Now, you're not going to be surprised when I tell you that relationships on ERDs are really relationship types with type instance semantics. Okay? And that's because instances of relationships do not appear on ERDs. Only the relationship type does. Let's look at that. Okay. So here we have an ERD over here, and we've got two entities, or entity types to be precise, but just like everybody else, I'm going to call them entities. And we've got one relationship type, just like everybody else, I'm going to call it a relationship. And the setup is player plays for team. These are all types, okay? Where are the instances? There are no instances in conceptual data models. There are no instances in any kind of ERD. Okay, where are the instances? Well, some people might say that the instances are out in the world that we're trying to model. They might say, well, you know, the team is the type, right? That's the entity type, and the instances are the real teams in the real world, so the Chicago Bucks, the Chicago Bulls, and the Milwaukee Bucks. Okay, that's one way of thinking about it, but it's not always particularly helpful to do that. I think the better way to think of it is, when would I have some kind of data technology thing that would include something in it that would be an instance? And that would be when you really implement the data store, okay, which we'll do quite often with a relational database. The team entity becomes the team table, okay? And in that table, there's a row for each of the instances of team. So there would be a row for the Milwaukee Bucks. There'd be a row for the Chicago Bulls. Okay. And then, the player entity would be implemented with the player relational database table. And there would be a row for each player. Okay. And here we're a little bit out of date. We have Michael Jordan, long retired, but I think it kind of tells you about my. When was the last time I was a big basketball fan? That's probably it. And in relational databases, some of you already know this, but uh, uh, others are going to learn in the future. We implement relationships with these things called foreign keys. So the team table has a primary key column, team ID, and the player table has a team ID column that's a foreign key. And by putting the value 2 in the foreign key entry in the row for Michael Jordan, we're pointing to the row 2 in the team table, which is for the Chicago Bulls. And this implements the instance of the relationship that connects Michael Jordan and the Chicago Bulls. So relationship instances happen in implemented data stores, okay? There's no such thing as a relationship instance on an ERD. ERDs are all about types. So they're about entity types, relationship types, even though we call them entities and we call them relationships. Now, Cardinality. Let's talk about that. Okay. Another quote from Andy Oppel. Cardinality rules determine how many instances of one entity may be associated with how many instances of some other entity. Okay, I don't think he said instances. I threw that in. Okay, so cardinality rules about how many instances of one can be associated with how many instances of other through relationships. Okay, how do we decide uh, how many there can be? Well, there maybe are some kind of rules kind of inherent in the physical world that we know. One of these is associated with many of those, or one of these or many of these are associated with many of those. Okay, so there probably are some kind of natural constraints on cardinalities, but most of them we're going to decide how many instances of one type can be associated with how many instances of another type by asking the users what the rules are in the business. So these cardinality rules that we're formulating are just the implementation of business rules that are the practice in the organization that we're building this solution for. Okay? So let's look at cardinality. I say here the notation occurs on each end of the relationship line. So let's look at how that's going to look. Okay, it looks like I forgot to shade the tops of these two boxes. So we have player plays for a team, and we haven't really talked about these symbols at each end of the line, and these are the cardinality notations. So how do you read this? Well, here's how I typically say to do it. Imagine yourself kind of walking around the diagram. Okay, so this is a big a game show stage with a painted floor. Okay, so you walk onto player and you look across the team and you read the cardinality symbol right up against a team. So you're standing on player and you ask the question, how many instances of team can be associated with one instance of player? So you're on player, you go, okay, for one instance of player, how many instances of team? You read it, one and only one. Okay. Now you walk around and you walk on the part of the painted floor that has the team entity, and you look across and you look at the cardinality symbols up against a player, and you ask, okay, for each instance of team, it can be associated with how many players? 0 to many. Okay? So, and let's think about whether we think that's right. For each team, how many players? Well, if we haven't assigned any players yet, if this is some kind of expansion team, well, it's not going to have any when we begin. Okay? And then it could have 1 or 2 or 3, or, depending upon how quickly we built the team. We might be doing this in the off season. When we get done, we'd have a whole complement of players. And now, when you think about it from the player side, how many teams does a player play for at any one instance? Well, one and only one. Now, how do we know that's true? Well, we ask the stakeholders for whom we're building the system, and we say, well, what are the rules? And they say, oh, well, the rules are you only play for one team at a time. Okay, so typically these cardinality rules are just the embodiment of the business rules that have been told to the data modeler by the people who operate the organization. Okay? So that's how that looks. Now, what are the possible symbols that we can see? Well, we saw most of them there. Okay, so we're just really looking at the right side of these. Okay, so this circle and a vertical line, 0 to 1. So that means it's optional. Okay, we might have an associated instance or we might not, 0 or 1. Okay, what's this? 0, this is the circle 2. We call this the crow's foot. This kind of cardinality notation is known as crow's foot notation. Okay, we read that for many. Okay, 0 to many. Still optional though. We don't have to have one, right? Okay, so we could have 0, we could have 1, we could have 2, we could have 1,000. 0 to many. Okay, 2 vertical lines, 1 and only 1. So it's required and it can only be 1. Okay, and then the last one, 1 to many. So it's required, but there may be many. Okay, so that's a pretty rich way of expressing how many instances can be associated with one instance from the other side. Okay? Okay, so let's do a little more looking at examples. Okay? In the same sense that we talk about how to read these cardinality indicators, okay, we also talk about the nature of the relationship between the two entities. Okay, so in general, one and only one, or 0 to 1, that's a 1 cardinality, and 1 to many or 0 to many, that's a many cardinality. So we kind of summarize the relationship between team and I think this should say player, not entity. Guess I was a little tired when I did that. Team and player of 1 to many. One team, many players. Okay, so that's a 1 to many. We usually get a lot of those in our data model. Many to many. Okay, so a typical instance of many to many would be something like employee and skill. So let's say we're a technical company and we want to represent we have a bunch of technical employees and they know kind of like programming language skills. So they know Java, they know Python, they know JavaScript, they know all those kinds of things. So one employee could have from 0 to many skills. So perhaps this isn't a technical employee, so they don't have any. Or they might have just 1 if they're kind of junior, or they might have 10 or 20, right? And then looked at the other way for each skill, say Python programming, okay, we might not have anybody on staff who knows it, especially if we're not a Python shop. Or we might have 1 or 2 or 3 or 20 or 40, okay? So this is a many-to-many relationship, okay? Now, let's go over and look at the next one, 1-to-1, okay? So let me back up. 1 to many, plenty of these. You're going to find plenty of these in the data model. Many to many. You're going to see some of these in the data model, okay? One-to-ones. Are you going to see a lot of these in the data model? Not as many as you might think. Okay. Okay, so let's look at three scenarios for one-to-one designs and talk about how common they might be. So, what about the relationship between employee and company car? Okay, so we're saying that this is basically one-to-one, but it's optional. Okay, so we're saying for each employee, it's associated with 0 to 1 company cars. Okay, so some employees are going to get company cars, and some are not. Okay, maybe the top executives are going to get company cars because they get a sweet deal, and maybe the sales people who drive around to see our clients are going to get company cars. But in general, say people who work in the office are not going to get company cars. Okay, so 0 or 1. And then we read it the other way. For each company car, it's associated with one and only one employee. Okay, and you might say, Kevin, what if this is a company car that hasn't been allocated yet? And I would say, oh, well, that's clever thinking. Maybe the left side should have said 0 to 1. Perhaps it should have been optional in both directions. Okay. Um, uh, hadn't thought of that before right now. Okay, so one-to-one optional. You'll see a number of these. Okay. Okay. What about one-to-one required? Well, I think you'll see fewer. One of the things that I could think of is, let's say, in this company, okay, each employee has a dedicated workspace. Okay, it might be a cubicle, it might be an office, it might be a suite of offices if they're really a big shot, right? So each employee, if I'm on the employee side, for each employee instance, we have one and only one workspace allocated to them. And for each workspace, we have one and only one employee. And then you might say something to me, Kevin, what if we have empty offices? We haven't allocated to any employee at all, or empty cubicles. And I might say, yeah, maybe there should be a 0 here too. Maybe this should be kind of optional in this direction. Okay. But you certainly can have one-to-one relationships between two different things that are not the same thing. The employee and the workspace are not the same thing. Okay. The last one I'm going to show you, I call one-to-one suspicious, which is whenever you have a one-to-one, you've got to be suspicious that these are really the same thing. Say they're two aspects of the same thing. Okay. And if we're doing another kind of data modeling, we're doing logical database design or physical database design, we might say, well, you know what? We're designing tables, and we don't want tables to be too big. So even if there are two aspects of the same thing, we're going to divide them up into two tables because that's a good implementation decision. I could see the argument for that. But conceptual data models are not physical implementations. They have a lot of magic. They have high magical power. Okay, so there's no reason to split up an entity because of implementation consideration. It either is the same entity or it's not. Okay, so here I've seen people design things where they have a product entity and then they have an inventory entity. And on the product entity, they'll record things like, oh, the product ID and the product name and the product description and the list price and those kinds of things. And then over on the inventory, what do? Well, they start with the product ID. That's always the hint that maybe you're talking about the same thing. It has the same identifier. Okay, and then they'll have things that have to do with the inventory, like quantity on hand. Inventory has this thing called economic order quantity, like how many you order at a time. Those kinds of things. Now, are these two different things? Well, they're two sets of considerations, but they're about the same thing. They're about the product. And so I would argue that this is one entity that we've divided up artificially. Okay, so whenever you see a one-to-one, the alarm should go off. You should ask yourself, is this really a one-to-one like the workspace? Or an optional one-to-one like the company car? Or is this just us taking kind of two aspects of the same thing and dividing them up when there's no practical reason for doing it? Okay? Because again, conceptual data models are high magic. Okay? So you don't have to say, well, then that's going to be too big of an entity. Well, the entity is what the entity is. If it's a big entity, it's going to get a big box. All right? There we go. Oh, so that's cardinality. Okay. And let's talk about one more thing here before we break the recording. Okay, we're going to talk about relationship degree. What do we mean by degree? Okay. Well, what we mean by relationship degree is how many entities are connected by a relationship. So let's look at these, okay? These are typical relationships that you're going to see on a conceptual data model. And they are easily implemented in a lot of technologies, including relational databases. And we call them binary. They have a degree of 2, so they're binary. Okay, so the coach's relationship is binary because it connects a coach and a team. The place for it is binary in that it connects a player and a team. Okay, so you might say, oh, Kevin, aren't all relationships binary? And my answer would be, well, in theory, not. Okay, it's just, so are all relationships binary? No. Okay. Are most relationships binary? Yes. Okay. So let's talk about another kind, unary. Okay, so if binary had one entity involved in the, two entities involved in the relationship, unary, meaning one, is only going to have a single entity. Okay, so it's the relationship between an entity and itself. So let's look at an example of that. So again, I have to remind you, even though I said an entity in itself, I really meant an entity type in itself, right? Because ERDs are all about types. They're not about instances at all. Okay, so can we really have a relationship between an entity and itself? Yes, we can. Now, why is this? Well, because the relationships are not really happening between the entity itself, but between instances of that entity. Okay, so here, the first example that we have is a person is married to a person. Okay, so what instances do we have the person type? Well, let's say, my wife and I were in there. So I'm Kevin, she's Brooke. Okay, so we one instance is Kevin, another instance is Brooke, and they're related to each other by an instance of an is married to relationship. All right, I can kind of see that on the diagram. On how would that work? How would that get implemented in a data store? Okay, well, in a data store, like a relational database, there'd be a person table. Okay, uh, and we would have a row for Kevin and a row for Brooke. Okay, and how would we point from one row to the other? We would point from one row to the other using a foreign key. Okay, now, would both of these have to point to the other one? No, in relational databases, we typically only point one way, and we have a way to travel that relationship back in the other direction. So we'd have the foreign key on one of them, and then the other one we would be able to figure out through this thing called a foreign key index. Okay? So we can have a relationship between the table and itself, even though that sounds absurd, because it's real. I said a table in itself. I meant an entity in itself. Um, it's really happening between the entity instances. And one of the reasons that the diagram maybe looks a little bit silly is we don't really have anything on the diagram that represents the instances, only the table. I'm sorry, only the entity. Okay, so sometimes it can kind of twist the mind. So this is a unary relationship because it's between an entity and itself, and it's one-to-one in that one instance is going to connect with one instance of this. Typically, at least in the US, we're married to one person at a time. Okay? Well, what about other things like this? Well, here's a really popular one. The relationship between employees and supervisors. Uh, so the entity is employee. Everybody who works for the company is an employee. Okay. Now, here's a case where it kind of helps to have two different names for the relationship. Okay. And I'll tell you why in a minute. So we can say an employee has a supervisor, and you follow that and you get to the supervisor. Or you can look at it from the other end. You can say the employee supervises, okay, and then you can go to the other end and you can see all the people that they supervise. Okay. Now, this has the potential to be a one-to-many, right? Okay, because we all know that it's typical for supervisors to supervise many people at once. Okay? And again, this is a relationship between the instances of the employee entity. All right? Now, these kind of relationships are said to be recursive. So how do we mean that? Well, we mean that in the same way that we mean recursive when we talk about recursive programming. Now, in my programming course at the iSchool at Illinois, we don't even cover recursive programming. It's the last of the chapters in the textbook, and I recommend to people that if they're interested in it, that they cover it on their own, that we cover recursive programming in intermediate courses. But what does it mean to be a recursive program? Well, essentially for a function to call itself. Okay. And if you're a programmer and you can kind of go, that's an interesting idea. But if a function were to call itself, wouldn't that go on forever? Wouldn't that be a sort of an infinite recursion? And the answer is no, because properly designed recursive programs it distinguish it between the average case in which we're going to keep on going and call ourselves, and the end case where we recognize this is the end and we're just going to stop. Okay? And that's the only reason that recursive programming will work, because we have to be able to recognize the end case. Well, it turns out that in supervisors and supervisees, we've got the same deal. We've got one person, typically in any organization, who's the boss. And so if you ask who their supervisor is, the answer will be no one. Okay, so you can kind of go round and round and round and round through the relationships and see who supervises who, but you should be confident that you'll eventually come to somebody who doesn't have a supervisor. Okay, and you should be equally confident that if you go in the other direction and you try to kind of explode out the paths of who supervises who, eventually you're going to come to people at the bottom who don't supervise anybody at all. Okay? So this ability to kind of think of this design being implemented over and over and over again, that's what gives its recursiveness. It's only practical because there are end cases in either direction to keep it from going on forever. Okay, so it's a pretty tricky design, but you can make it work. And there are lots of data stores that include this unary one-to-many design. Okay, now there's actually even data models that have unary many-to-many designs. Okay, that's a little bit wilder, but it works out. So on one side, typically we use this kind of design where we have parts and subparts. So let's say we're a manufacturing company, and we build things. So we assemble parts into things that we sell to customers, right? And sometimes while we're doing that, we'll build 2 or 3 or 4 parts into a subpart, and maybe into an assembly, and maybe we'll use that assembly in 2 or 3 different products. Okay, so when you're going through the relationship from the is subpart of side, well, then you can find all the things that this part is used in. Okay, and when you're going through the relationship from the has of subpart side, then you're going to find all the things that are components of the current part, all the things you'd have to have in order to assemble it. Now, both of these seem like they could go on forever, but they do end, right? So if we're working up towards, from the subparts to the parts, eventually we get to a part that doesn't get included in anything as a subpart. We sell it as itself. The example that I'd like to make is the Easy Bake Oven, right? So the subparts are, the light bulb and the door and all this kind of stuff. So they're all subparts, and they may have subparts, but as we go up the chains, we eventually come to the easy bake oven, and we actually sell that. Okay. Could that be a part of a bigger set that includes the easy bake oven and something else? Yeah, that's possible. Maybe the easy bake oven is a subpart of the grand kitchen set, right? But sooner or later, you'll come to something that we sell just as is. Okay. And then as you go down through the hierarchy, well, you eventually come to something like a screw or a light bulb or, some part that we buy it as it is. Okay. We buy the light bulb from the light bulb company. We buy the screw from the screw company. We don't buy subparts and assemble them. Okay. So again, this kind of unary many to many is a recursive design because it can run around and around for several levels, but it's only practical because we know that these chains of relationships are going to end. Okay? So, how many times will you have a unary relationship in your data model? Well, as a beginner, maybe none. Okay? But as you begin to model things that are more and more challenging, they'll start to creep in. Okay? Now, we've had binary relationships. We've had unary relationships. Uh, what about three-part or four-part? Three-part would be called ternary relationships. Well, you can take it from me as a guy who's worked with technologies that can implement uh, ternary and higher order relationships, that in those technologies, uh, we don't even use them. Okay? So most practical data modelers, regardless of what kind of um, technology they expect to implement the data store in, even if it could represent ternary or higher relationships, they're such a pain in the butt that they don't. So we're left with binary and unary. So mostly binary, okay? Mostly binary. The occasional unary, okay? And it turns out that any higher order relationships can be turned into a combination of binaries. And that's the reason why people don't fool with three-way relationships and four-way relationships. It's easy to think of them, but it turns out that it's not worth the trouble. They're kind of a train wreck. Okay? So we're going to stop there, and we'll be back soon with attributes.